Hello, my dear students. Welcome to my YouTube channel, Shiv Academy of Mathematics. So, in today's video lecture, I am going to discuss about the convergence of the beta function. Or we will show that the integral 0 to 1 x to the power m minus 1, 1 minus x to the power n minus 1 dx exists if and only if m and n both are positive. Because this is the definition of beta function, integral 0 to 1 x to the power m minus 1, 1 minus x to the power n minus 1 dx. So let us start the solution. How we can show that this beta function converges whenever m and n both are positive. So my dear students, let us take this integral is equal to I. Let us take this integral is equal to I. So what is I? I is integral 0 to 1 x to the power m minus 1, 1 minus x to the power n minus 1 dx. X to the power m minus 1, 1 minus x to the power n minus 1 dx. So, my dear students, if we take m greater than equal to 1 and n greater than equal to 1, if we take m greater than equal to 1, n greater than equal to 1, then this integral I is proper integral. Then this integral I is proper integral. And if it is proper integral, that means to say it is convergent. It is convergent. That means to say whenever both m and n are greater than equal to 1, then the given integral I is convergent, being a proper integral. Okay. So now we have to check the case whenever m and n both are less than 1. Both m and n are less than 1. So look at this I. If I am saying m is less than 1, means to say I am saying m less than 1, that means to say m minus 1 is less than 0. In that case, 0 will be the point of infinite discontinuity. 0 will be the point of infinite discontinuity. And if n is less than 1, here 0 is the point of infinite discontinuity. 0 is the point of infinite discontinuity. And if n is less than 1, that means to say n minus 1 less than 0. In that case, 1 is the point of infinite discontinuity. So basically what we have to check in this case, whenever m and n both are less than 1, then what happens with this beta function? Is it convergent or divergent? So let us start. Keeping in mind that if m is less than 1, then 0 is the point of infinite discontinuity, and if n is less than 1, then 1 is the point of infinite discontinuity. So we can write here 0 is the point of infinite discontinuity. 0 is the point of infinite discontinuity if m is less than 1 and 1 is the point of infinite discontinuity if n is less than 1. If n is less than 1. So my dear students, for the case m less than 1 and n less than 1, we divide the given integral into two parts. We take a suitable number between 0 and 1, and 1 by 2 is the suitable number between this 0 and 1. But you can take other number also other than 1 by 2. But here I am taking the number 1 by 2 between 0 and 1. That means to say we are taking this I is equal to 0 to 1 by 2 x to the power m minus 1 1 minus x to the power n minus 1 dx plus integral 1 by 2 to 1 x to the power m minus 1 1 minus x to the power n minus 1 dx. So this integral I is converted into two integrals. First one is 0 to 1 by 2, second one is 1 by 2 to 1. So let us take the first integral as I1, second integral as I2. This integral 0 to 1 by 2 is I1, second one is I2. So we discuss the convergence of I1 and I2 separately. So first of all, we discuss the convergence of I1, it is 0 to 1 by 2 x to the power m minus 1 1 minus x to the power n minus 1 dx. So my dear students, what we are going to do here, we are checking, because x equal to 0 is the point of infinite discontinuity, and here m is less than 1. M is less than 1. So in this case, what we do, let us take this as 0 to 1 by 2 fx dx. So fx is what it is? X to the power m minus 1 into 1 minus x to the power n minus 1. This is fx. So just like in my previous video, I discussed one problem of this improper integral, in which we have checked that it is convergent or divergent. So we applied the comparison integral. So we apply the same result here also. So for that, what we have to do, we have to choose another function gx. So in that video, I also told you that how we can choose the function gx. So basically this x to the power m minus 1, because we are saying that x equal to 0 is the point of infinite discontinuity. So we choose the function x according to this. So what we write? We write function fx in another way. So we write here it in this way: 1 minus x to the power n minus 1 upon x to the power 1 minus m. You know very well that m is less than 1. So 1 minus m is greater than 0. So you have to keep in mind one thing, that we have to take this x to the power m minus 1 in the denominator, or 1 minus x to the power m minus 1 in the denominator. If x equal to 0 is the point of infinite discontinuity, then we take this term in the denominator, and if when we discuss the second case, 1 by 2 to 1, we take this 1 minus x to the power n minus 1 in the denominator, due to the points of infinite discontinuity. So this is the main key or main point to solve this problem. So what we do now, we take gx as this 1 upon x to the power 1 minus m. So let us take gx is equal to 1 upon x to the power 1 minus m. Gx is equal to 1 upon x to the power 1 minus m. So now we compute the limit x approaching to 0 plus. So therefore, limit x approaching to 0 plus fx upon gx is equal to. So how we compute this? It is limit x approaching to 0 plus, because fx is what? X to the power m minus 1 into 1 minus x to the power n minus 1, or rather you say 1 minus x to the power n minus 1 upon x to the power 1 minus m. So when we divide this term by this gx, so this x to the power 1 minus m will cancel out. So we are having just only one term, it is 1 minus x to the power n minus 1. And when we put the limit x equal to 0 plus, so it is 1 minus 0, so it is 1 is to n minus 1, so it is 1, which is non-zero and finite. So my dear students, One more thing, when we apply, just like in infinite zero also, the comparison test. So this limit fx by gx must be non-zero and finite. Non-zero and finite. After that, what we say that this integral, there are two integrals. One we take with g and second we take with this f. That means to say I1. So what we say from here? Therefore, integral 0 to 1 by 2 gx dx and this integral I1 converge or diverge together. Converge or diverge together. One more language you can write that they behave alike. They behave alike. Or rather you can write both converge or diverge together. Now this integral gx, but integral 0 to 1 by 2 gx dx equal to 0 to 1 by 2, dear students, there was a technical issue in between the video. So this 0 to 1 by 2 gx dx is equal to 0 to 1 by 2. What is the value of this gx? Gx was 1 upon x to the power 1 minus m. Or what you can say, it is 0 to 1 by 2 dx upon x minus 0 to the power 1 minus m. So yesterday I uploaded a video regarding this comparison integral and important comparison integral. In that video I told you that if we are having a to b dx upon this x minus a to the power m, and if this a is the point of infinite discontinuity, means to say this lower limit, so this integral is convergent. This integral is convergent if this m is less than 1. Similarly, I discussed that integral a to b dx by b minus x to the power m is also convergent if m is less than, or you say it n when n is less than 1. So we apply this result here. So if you take this a is 0, so it is a, that is 0. So it is convergent according to that result whenever, but this is convergent. So what we are saying, it is convergent at x equal to 0, if and only if 1 minus m is less than 1, because what I am saying, this m must be less than 1. So this m is here 1 minus m. So this 1 minus m must be less than 1. That is, if and only if we take m to the right side, 1 to the left side, so what we are getting, m is greater than 0. So according to this comparison test, so I1 is convergent at x equal to 0, if and only if 0 less than m less than 1. So m greater than 0 from here, and we started from here m was less than 1. So we have combined these two conditions whenever m is greater than 0 and less than 1. So in this way we can prove that this integral I1 is convergent at x equal to 0 if and only 0 less than m less than 1. So what remains? It remains to check the convergence of this integral I2, that is 1 by 2 to 1 x to the power m minus 1 minus x to the power n minus 1 dx. So again what we do now to check the convergence of I2 is what? 1 upon 2 to 1 x to the power m minus 1 1 minus x to the power n minus 1 dx equal to, again I am taking 1 by 2 to 1 fx dx at x equal to 0 when n is less than 1. So we have to check the convergence of this integral I2 at x equal to 0 when n is less than 1. So again this fx, again what we have to do, we have to choose gx. So again we are writing here fx is equal to x to the power m minus 1 minus x to the power n minus 1. So just I discussed in the first case that we have to pick gx in a way that according to the point of infinite discontinuity. That's why now we are writing it as x to the power m minus 1 in the numerator and this 1 minus x to the power 1 minus n in the denominator. Why? Because n is less than 1. So this is the way to choose or pick another function gx from here. So what we do, we take gx. So what we do now, let gx is equal to 1 upon 1 minus x to the power 1 minus n. So this is the gx. So we divide this f by g and again we take the limit. Now x approaching to 1 minus, there we were taking 0 plus, and because here 1 is the upper limit, so what we do, we take x approaching to 1 minus fx upon gx. All these things I have discussed in my previous video, that when we have to take 0 plus or this 1 minus or a plus or b minus according to the limits, upper limit and the lower limit. So what we do here, we write it as limit x approaching to 1 minus. So here it remains only x to the power m minus 1. Because this 1 minus x to the power 1 minus n cancel out from this f and g. So when we put here x equal to 1, so we are getting again the limit as 1, which is non-zero and not equal to infinite, means to say finite. You can write non-zero and finite, or you can write not equal to 0, not equal to infinity. So again what we write, so this integral 1 by 2 to 1 gx dx and I2 converge or diverge together. So these two integrals I2 and this integral 1 by 2 to 1 gx dx converge or diverge together. But if again we look this integral gx, but this 1 by 2 to 1 gx dx equal to integral 1 by 2 to 1, and value of this gx is 1 upon 1 minus x to the power 1 minus n, is convergent at x equal to 1 if and only if 1 minus n is less than 1. Convergent at x equal to 1 if and only if 1 minus n less than 1. That is n is greater than 0. So finally, dear students, what we can say that so I2 is convergent. So I2 is convergent at x equal to 1 if and only if again n is greater than 0 but less than 1. N is greater than 0 and less than 1. That means to say, when we combine both these two integrals I1 and I2, so what we can say that the integral I is convergent if and only if 0 less than m less than 1 and 0 less than n less than 1, and also it is proper integral for m greater than equal to 1 and n greater than equal to 1. That means to say we can say that this I is convergent whenever both M and N are positive. So finally what you have to write, when we combine, because this I was the combination of I1 and I2. First case we have discussed, whenever M and N are greater than or equal to 1, then this integral is proper, it is convergent. Whenever M less than 1, N less than 1, but greater than 0 in I1 and I2, we have discussed that both these integrals are convergent whenever 0 less than M less than 1 and 0 less than N less than 1. So basically we are getting the convergence 0 less than M less than 1, M greater than or equal to 1, 0 less than N less than 1, N greater than or equal to 1. For these two cases, the integral I was proper, and for these two cases we have discussed separately. For this case we have taken I1, for this case we have taken I2. So this is a very important result in this UG mathematics. Either you are from non-medical or mathematics honors, or you are a BTech student. So in this way we can check the convergence of the beta functions. So thank you for watching the video, and for more videos related to mathematics, don't forget to subscribe our YouTube channel Shiv Academy of Mathematics. Thank you dear students.